Two machines, each one the height of a 5-story building, grinding through the seabed in opposite directions. 10 kilometers of darkness, salt, pressure, and mud. And somehow, they had to meet in the middle. Welcome back to the channel. What you are about to see is one of the most extraordinary highway construction projects ever attempted by human engineering. It is called the Tokyo Bay Aqua-Line, and the story of how it was built is almost impossible to believe. This is not just a road across a bay. It is a road that starts on land, plunges beneath the ocean floor, travels nearly 10 kilometers under the sea, surfaces onto an artificial island that did not exist before engineers created it. One continuous highway, two completely different engineering systems connected by a man-made island in the middle of Tokyo Bay. Consider the obstacles. Tokyo Bay is one of the busiest shipping channels in the world. Thousands of cargo vessels, tankers, and ferries cross it every day. Above, the flight path of Haneda Airport, one of the busiest airports on Earth, passes directly over the western shore. The seabed is soft, unstable, saturated with water. Earthquakes strike the region regularly. Typhoons batter the coast every summer. The water is deep, the currents are strong, and the geology is unforgiving. And in the middle of all of this, someone decided to build a 15-kilometer highway from Kawasaki to Kisarazu straight across the bay. Before we continue, make sure to subscribe to the channel and hit the notification bell so you never miss a new video. Stay with us until the end of this one. Because what happens beneath the surface of Tokyo Bay, what millions of drivers never see, is far more extraordinary than the road itself. This story begins not in 1989, when construction started. It begins decades earlier. In the 1960s, Japanese engineers and urban planners first proposed the idea of crossing Tokyo Bay with a fixed road link. At that time, driving from Kawasaki on the western shore to Kisarazu on the eastern shore meant going all the way around the bay, a journey of approximately 90 minutes through some of the most congested urban corridors in the world. A direct crossing would reduce that to roughly 15 minutes. The economic argument was overwhelming, but the engineering challenge was staggering. For more than 20 years, the project existed only on paper. Studies were conducted, proposals were drafted, revised, and redrafted. The question was never whether Japan needed this crossing. The question was whether it was even possible to build one. At first, there was only water. No road, no tunnel, no island. Just the gray, restless surface of Tokyo Bay stretching from shore to shore, fishing boats, container ships, and beneath them, a seabed that had never been disturbed by anything larger than an anchor. The first and most fundamental problem was this: you cannot simply build a bridge across Tokyo Bay. On the western side, near Kawasaki, the airspace belongs to Haneda Airport. Bridge towers would interfere with flight paths, and the shipping lanes on this side of the bay are among the densest in Japan. A bridge with tall pylons would create an unacceptable hazard for both aircraft and vessels. On the eastern side, near Kisarazu, the shipping traffic is lighter, and the airspace is less restricted, so a bridge becomes feasible. But on the western side, the road had to go under the water. If you build only a tunnel, the entire 15-kilometer crossing becomes enormously expensive and complex. If you build only a bridge, you violate airspace restrictions and endanger maritime traffic. Neither solution works alone. So the solution was not a tunnel. It was not a bridge. It was both a tunnel on the western side, a bridge on the eastern side, and an artificial island in the middle where one becomes the other. 3 completely separate engineering projects fused into a single continuous highway. This was the Tokyo Bay Aqua-Line. The project was managed by the Tokyo Bay Highway Corporation, and construction officially began in 1989. The final cost reached approximately 1.44 trillion yen, roughly 11 to 14 billion US dollars. Depending on the exchange rate at the time, this made it one of the most expensive single pieces of road infrastructure ever built. The first challenge was the tunnel, nearly 10 kilometers long, 2 parallel tubes, one for traffic heading toward Kisarazu, one for traffic heading back toward Kawasaki. Each tube large enough to carry 2 lanes of highway traffic, plus emergency walkways, ventilation ducts, utility conduits, and safety systems. The tunnel needed to withstand the crushing pressure of the water above, the instability of the seabed around it, and the seismic forces that regularly shake this part of Japan. To bore these tunnels, engineers deployed massive shield tunneling machines, tunnel boring machines of extraordinary scale. Each machine was approximately 14 meters in diameter. Picture a cylinder nearly 5 stories tall, fitted with a rotating cutting face, studded with hardened steel teeth, hydraulic rams pushing it forward meter by meter, and an automated system behind it assembling pre-cast concrete tunnel segments into place. These were among the largest tunnel boring machines operating anywhere in the world at that time. The machines began their work from both ends, one set launching from the Kawasaki shore, the other from the site of the future artificial island in the middle of the bay. They would bore toward each other through kilometers of soft marine sediment, clay, sand, silt, and gravel beneath the seabed. Every meter mattered. Every degree of alignment mattered. Imagine the conditions inside these tunnels during construction. The machines pushed forward through ground saturated with seawater. The pressure was immense. Workers operated in an environment of constant noise. The grinding of the cutting head against rock and sediment, the hiss of hydraulic systems, the clang of steel segments being lifted into position by cranes inside the tunnel. The air was hot, humid, and heavy with dust. Ventilation systems worked continuously to keep the atmosphere breathable. Behind the cutting face, crews worked around the clock, assembling the tunnel lining. Prefabricated reinforced concrete segments, bolted together ring by ring, sealed with gaskets to prevent water ingress. Each ring of the tunnel was assembled from multiple curved segments. Each segment had to be manufactured to precise tolerances. Millimeters mattered at this scale because even tiny misalignments would compound over kilometers and result in a tunnel that curved off course or failed to meet its counterpart boring from the opposite direction. The segments were transported down the length of the growing tunnel. On-rail systems lifted into place by erector arms, mounted on the tunneling machine, and bolted together while the machine continued to push forward. Then came the waterproofing. A tunnel beneath the sea is only as good as its ability to keep the sea out. Waterproof membranes were applied. Grouting was injected behind the tunnel lining to fill any voids between the concrete segments and the surrounding earth. Drainage systems were installed to collect any water that did seep through and channel it to pumping stations that would operate continuously for the life of the tunnel. Without these systems, the tunnel would flood. With them, it remains dry enough for vehicles traveling at highway speeds. Then came the ventilation challenge. A tunnel nearly 10 kilometers long, carrying tens of thousands of vehicles. Per Dalton Y, each one producing exhaust fumes without ventilation, the air inside would become toxic within minutes during peak traffic. The solution was a comprehensive ventilation system running the full length of both tunnel tubes. Fresh air is drawn in. Exhaust air is extracted. The system involves massive fans, air ducts running above and below the roadway, sensors monitoring air quality in real time, and control systems that adjust fan speeds based on traffic density. Part of this ventilation system relies on one of the most striking structures in all of Tokyo Bay, the Kaze no T, the wind tower. This is a ventilation shaft rising from the surface of the bay, separate from the Umihotaru island, designed to draw fresh air down into the tunnel and expel contaminated air upward. The wind tower is not just functional, it is architectural. Its sleek, curved form rises from the water like a sculpture, visible to ships passing through the bay and to passengers on flights descending into Haneda. It is one of the few parts of the Aqua-Line that is visible from the surface, a hint of the enormous hidden infrastructure below. Then came the artificial island, Umihotaru. The name means sea firefly. After the bioluminescent creatures found in the waters of Tokyo Bay, this island did not exist before the Aqua-Line project engineers created it from nothing, or rather from millions of tons of material deposited on the seabed until solid ground rose above the waterline. The island is approximately 650 meters long and roughly 100 meters wide. It sits in the middle of Tokyo Bay, halfway between Kawasaki and Kisarazu. Its purpose is both structural and functional. Structurally, it is the point where the tunnel ends and the bridge begins. Traffic emerges from the tunnel tubes, enters the island, transitions to the surface level, and continues onto the bridge. Functionally, it serves as a rest area. Parking, restaurants, shops, observation decks. Drivers can stop here, stretch their legs, and look out over the bay in every direction. To the west, they can see the skyline of Kawasaki and Yokohama. To the east, the shore of Chiba. And directly below their feet, the tunnel continues its silent work. Building this island required constructing massive steel and concrete caissons. Enormous hollow structures sunk to the seabed to form the island's perimeter walls. These caissons were fabricated on shore, towed into position by tugboats, carefully aligned, and then sunk by flooding their internal chambers with water. Once in position, they were filled with sand, gravel, and rock. The spaces between and behind them were filled with dredged material, compacted and stabilized to form solid ground. Layer by layer, the island rose from the water. Retaining walls, drainage systems, foundation piles, structural slabs, utility conduits, electrical systems, plumbing, fire suppression systems, elevator shafts, stairwells, ventilation ducts, all of it built on ground that had not existed a few years before. Then came the bridge from Umihotaru eastward to Kisarazu. The highway crosses approximately 4.4 kilometers of open water on a multi-span bridge. This section was possible because the eastern side of the bay has fewer restrictions, lower shipping traffic density, no airspace conflicts with Haneda. The bridge was constructed using large prefabricated girder sections, supported on piers driven deep into the seabed. Each pier foundation had to be designed to withstand not only the weight of the bridge and traffic above, but also the lateral forces of currents, waves, wind, and crucially, earthquakes. Japan sits on one of the most seismically active zones on Earth. The entire Aqua-Line tunnel, island, and bridge had to be engineered to survive major earthquakes. This meant flexible joints in the bridge spans that allow movement without fracture. It meant tunnel segments designed to absorb and distribute seismic forces. It meant the artificial island itself being engineered to settle and shift without structural failure. Every component, every connection, every joint was designed with seismic resilience as a fundamental requirement, not an afterthought. The bridge piers were constructed using a combination of driven steel piles and cast-in-place. Cofferdams were built around each pier location, temporary enclosures that held back the seawater, while workers built the foundations in relatively dry conditions. Steel reinforcement cages were assembled, concrete was poured, and the piers rose from the water one by one. Once the piers were complete, massive precast concrete and steel girder sections were lifted into place by floating cranes, some of the largest marine cranes operating in Japan at the time. Each girder section was positioned with precision, connected to its neighbors, and secured. The bridge deck was then finished with asphalt, lane markings, barriers, lighting systems, drainage grates, expansion joints, sensor cables, and emergency telephone stations. Then came the electrical and control systems. The Aqua-Line is not just concrete and steel. It is a living, monitored, controlled environment. Throughout the tunnel, sensors track air quality, temperature, humidity, wind speed, traffic flow, and structural integrity. Cameras cover every meter. Fire detection systems, heat sensors, smoke detectors, flame detectors are embedded in the tunnel walls and ceiling. Fire suppression systems, including water spray nozzles and foam generators, are pre-positioned throughout the tunnel length. Emergency evacuation routes connect the two tunnel tubes, allowing passengers to escape from one tube to the other in case of fire or accident. Emergency lighting operates on independent power supplies. Communication systems link the tunnel to a central control room that monitors operations around the clock. Every day of the year, then came the testing. Before a single civilian vehicle entered the tunnel, every system was tested. Ventilation fans were run at full capacity. Fire suppression systems were activated. Evacuation drills were conducted. Traffic management systems were tested with convoys of vehicles. The bridge was load tested. The tunnel alignment was verified one final time. Every bolt, every seal, every cable, every sensor, every drain, every light, every fan, every camera, every emergency telephone, all of it checked, verified, and certified. On the 18th of December 1997, the Tokyo Bay Aqua-Line opened to traffic. A journey that once took 90 minutes now took 15. Two cities separated by an entire bay were suddenly connected by a single continuous highway. But the story did not end there. The initial toll was set at approximately 4,000 yen for a standard passenger car. This was expensive, far more than most Japanese drivers were willing to pay for a daily commute. Traffic volumes fell dramatically short of projections. The Aqua-Line, for all its engineering brilliance, faced serious financial difficulties. The road was a marvel. The economics were a problem. Years later, Chiba Prefecture intervened, starting around 2009. The prefecture began subsidizing the toll for vehicles using the ETC electronic toll collection system, reducing the effective price to approximately 800 yen. Traffic surged. The communities on the Chiba side of the bay experienced economic revitalization. What had been a financial cautionary tale became a case study in how toll pricing affects infrastructure usage. Most drivers who use the Aqua-Line today see only the road. They see asphalt and lane markings and overhead lights. They do not see the tunnel boring machines that chewed through 10 kilometers of seabed in the dark. They do not see the thousands of concrete segments assembled ring by ring in conditions of crushing pressure and relentless humidity. They do not see the waterproof membranes holding back millions of tons of seawater just meters from their windshield. They do not see the ventilation fans spinning ceaselessly to keep the air breathable. They do not see the seismic joints flexing invisibly with every tremor that passes through the earth beneath Tokyo Bay. They do not see the pumps that run day and night, every day, every year, removing the water that constantly tries to reclaim the space humans carved from the seabed. They do not see the control room where engineers watch every camera feed, every sensor reading, every temperature gauge, every air quality measurement keeping this invisible highway alive. They see a road. They drive across it in 15 minutes, and they have no idea what it took to build it. The Tokyo Bay Aqua-Line is not a road. It is a statement. A declaration that when human beings commit their knowledge, their labor, their ambition, and their courage to a single purpose, there is almost nothing they cannot build. Beneath the ships, beneath the waves, beneath the flight paths and the fishing boats and the gray surface of the water, there is a highway, and every meter of it was earned. If you enjoyed this video, subscribe to the channel and turn on notifications so you never miss our next deep dive into the world's greatest engineering projects. Leave a comment and tell us, would you drive through a tunnel 10 kilometers under the sea? Thank you for watching. We will see you in the next one.